Good afternoon, everyone. My name is Zhang. I'm a fourth-year PhD student in biostatistics from UPenn. And today my topic is about NCO-Calibrated DID analysis. So let's first go over a real-world case study. And we know the racial ethnic disparities have been long-lasting in the healthcare. And when the pandemic comes, a paper published talk about the COVID-19 association with the racial ethnic disparities. And a more important research question would be, does the pandemic worsen the racial ethnic disparities? To answer this question, a difference in difference approach can help find the racial ethnic disparities attributable to the pandemic while controlling from the pre-existing disparities. And here the picture shows how it works. So first, the red line showed the prevalence of outcome for the minority racial group, and the blue line showed the non-Hispanic white group, and the purple area would be the racial ethnic differences after the COVID-19 infection. Similarly, the difference can help identify the pre-existing racial disparities, shown in this picture as gray area. So in this way, the difference or DID can help identify the racial ethnic difference attributed to the COVID-19 infection. However, it has a key assumption, which named the parallel trends assumption. And the parallel trends assumption stated that in the absence of the intervention, the before intervention difference and the after intervention difference should be the same. And this means that in the plot, the green area before and after is equal to the counterfactual outcome differences. However, in the reality, this may not be scientified, and because of the system bias from the unmeasured confounding variables. And here's the picture show the real scenario. So the system bias shown in the gray area, it is not identified, and thus we cannot use the difference analysis to identify the racial ethnic difference attributable to COVID-19 infection. And how to calculate it? So you guys may already heard the legend this morning. And so the legend used the empirical calibration. And here's the landmark paper on the PNAS. And it used the negative control outcome. And it is known in priori to be unrelated to the exposure. And the legend study, for example, used the Ingronel as one NCO that is known to be unrelated to the anterior hypertension. And a recent published paper from our group, we used the OHDSI framework to calibrate the symptom bias. And here's the example of the 40 NCOs. And here's the list of all the NCOs. So our question is that, can we make an empirical calibration for the DID model? And here's our proposed method, NCO-DID. So in the step one, we used a DID model on the cohort by using the outcome of interest as the outcome. The beta 3 would be the parameter of interest. And step two, we fit the DID model for an NCO. And step 3 would be empirical calibrate. So from this proposed method, you may ask the question, why the estimation from the DID model for an NCO is equivalent to the estimation for the system bias? And here's the reason. So we can write down an estimating equation for the outcome of interest, and it has two parts. The first part would be the system bias for the outcome of interest, and the beta 3 would be the trivial size. And similarly, we can write down the estimating function for the NCO, and it also has two parts. It will be the system bias for the NCO plus the trivial size. And we know because of the NCO, the trivial size should be 0. And we also make assumption that the system bias for the NCO is equal to the systematic bias for the outcome of interest, so that we have this equation. That is, estimation of our 3 hat is approximately equal to the system bias for the outcome of interest. And in this way, we're able to calibrate the system bias. And in reality, we leverage M NCOs, just like the example I showed you for 40 NCOs for the vaccine study. And here's the comparison. So the baseline method would be the traditional DID model, and our proposed method, we have one more step to use the empirical calibration. And here we made an empirical evaluation from different symbol sets from 1,000 to 3,000. And the before calibration, the gray box plot showed the traditional DID model, and the orange box plot showed the proposed method. So you can see that across all the scenarios, the proposed method can have a smaller bias to the true size, and also it has a better coverage probability. So our key message is that across all the scenarios, the proposed NCO DID model successfully calibrates the systematic bias. And for the real-world case study, it is now under revision at the Nature Communications. So our takeaway message is that, first, we extend the OHDSI empirical calibration framework for the DID model, and secondly, it helps to control the systematic bias from the unmeasured confounding variables. And third, in the real-world case study, it helps to understand the racial ethnic difference in long COVID conditions after COVID-19 infection. And here's my acknowledgement. My poster would be number 118, and you are welcome to ask questions. And the first QR code is for my code, and the second QR code is for my Google Scholar page. So if you have any questions, you can feel free to email me. And by the way, I'm on the job market, so if you have any questions, you can also feel free to email me. Okay, thank you.